Here are two vector spaces. In this episode, we'll define how to construct their tensor product space in a visual way. We'll avoid using components as much as possible. To simplify the visualizations a little, we'll work with two-dimensional spaces, but everything we show extends to more dimensions as well. We'll pick a blue vector and a red vector. At first, we'll choose unit vectors. We'll combine them together to create a new object as follows. We'll draw a unit circle, put the blue vector inside, and the red vector at its tip. We'll add copies of the red vector all around the circle, except that as we move away from the original position, they diminish in length, and at the back, they're flipped. Let's define this rule more precisely. Here's an arbitrary direction vector. We'll project it onto our original blue vector and measure the length of the projection. This can be viewed as the length of the shadow it casts on our original blue vector if there's light coming straight from above it. The red vector at this location on the circle is a copy of our original red vector but scaled by 0.6. Closer to our original blue vector, the scaling factor gets closer to 1. And if we move further away, it diminishes. Beyond 90 degrees, it becomes negative, and at the exact opposite, it is -1. And this is our result. Finally, we'll hide the original blue vector. We'll call the resulting object a simple tensor. It is a unit circle with two patches of red arrows pointing in opposite directions. We'll say that this object is the tensor product of our two input vectors. Let's show another example. The blue vector is now a unit vector pointing in the x direction, and the red vector is some arbitrary unit vector. And we'll compute their tensor product. Here's an example direction again. Anywhere on the right side, we get positive scaling factors and negative on the left. And here is the result, another simple tensor. So we always get two patches of red arrows. The red input vector controls the direction one patch is pointing towards, and the blue input vector controls where the center of this patch is located. Next, we need to explain what happens if the inputs are not unit vectors. If we change the length of the red vector, then the answer is simple. Our construction rules work in the same way. We have scaled copies of our input red vector all around the circle. The resulting object is another simple tensor. The effect of changing the length of the blue vector is less obvious. One guess is that it will change the size of our circle. But we want all our tensors to be represented by a unit circle. So we'll define that scaling the blue vector has the same effect as scaling the red vector. It also changes the length of the tensor's red vectors. We'll soon explain why we actually have to define it this way. So we have defined the tensor product of two vectors. Now we are ready to define the meaning of the tensor product of two vector spaces. The result is a new space filled with tensors. Initially, we populated it with all possible simple tensors. These are all the tensors we can create by computing the tensor product of pairs of vectors in the way we just saw. All of them have the same general structure, two opposite patches of red arrows, and all the red arrows are aligned. We now need to equip our newly created space with operations. Let's start with the scaling operation. For example, let's multiply this simple tensor by the scalar factor 0.5. We apply this scaling operation to each red vector. The result is some other simple tensor that is already in our space. Next, let's add two simple tensors together. We'll add each pair of red vectors that landed at the same spot. Here's an example pair. We'll add them as ordinary vectors, put one at the end of the other, and draw a new vector from start to end. We'll repeat this at all other locations, and here's the result. We can see that this is a new type of tensor. The red vectors are not all aligned. They point in different directions. We'll call it a non-simple tensor. We'll add it to our space, along with all the other non-simple tensors we can create using addition. Let's look at this one, for example, and demonstrate how to create it. We'll take two unit vectors pointing in the x direction and construct a simple tensor. We'll also create a simple tensor from two unit vectors pointing in the y direction. Adding them together, we'll get the non-simple tensor we want. Let's prove it. Let's pick an arbitrary direction vector. Starting on the right, we'll draw its projection. The red vector at this location is a copy of the input red vector, scaled by the length of the projection, so the result is identical to the projection. The same is true for the second tensor. The red vector here is identical to the projection. Now let's add the two together. The sum of the two projections is equal to our direction vector, and so the sum of the two red vectors is equal to it as well. And this is true everywhere, of course. The tensor we wanted actually had smaller red vectors, which means we should have scaled down our inputs a little. Here's a recap. We started with two vector spaces and constructed their tensor product space. This space contains objects called tensors, and there are two different types. Simple tensors are created directly by taking two vectors and computing their tensor product. Non-simple tensors can't be generated directly by any two vectors, but are the sum of simple tensors. We'll soon continue discussing the properties of this visual construction. But now let's revisit the physics example from the previous episode. Here's a recap. This is a qubit, a basic unit of information used in quantum computers. We model its state using a two-dimensional vector space. We actually need to use a vector space over the complex numbers, but we simplify and use real numbers. We label the axes on and off instead of the usual x and y. The qubit's state is represented by a vector. If it's pointing in the off direction, then the qubit is off. And if it's pointing in the on direction, then the qubit is on. In between, it's in superposition. Instead of a single definite value, we get a probability distribution. The probabilities are given by the vector's components, except we need to square them first. So here, the probabilities are 64% and 36%. According to quantum physics, every vector in this space defines a possible state of the qubit. This space is therefore also called a state space. The length of the vector is meaningless. If we get a vector that is not a unit vector, we'll simply normalize it first. We can't observe a qubit directly, but we have a measurement device. The device has only two possible outcomes, on or off. If the qubit is in the on state, then the device will detect on. And similarly for the off state. In a superposition, it is common to say the qubit hasn't made up its mind yet if it is on or off. That's why we can't predict what the measurement outcome will be. We only have probabilities. When we measure, the qubit does make a decision. We got an on result. Also, the state of the qubit snapped in accordance with the observed result, and now it is in the on state. A second measurement will surely produce the same result. Let's show another example. This state specifies a 50-50 distribution. This time off was randomly picked, and this is our qubit's new state. We have explained how a qubit works using this abstract mathematical representation. Of course, there is some physical system behind this, but the implementation details are not important for this video. Next, let's show what happens when we tilt the device. The coordinate system in the state space has rotated too. We rotated it by the same angle as the device, though in real life the relationship might be more complicated. Now let's see what this means. The qubit's state vector remained the same, but it has different components now according to the rotated coordinate system. So if we measure at this angle, we get different probabilities. Here's another example. When using the ordinary coordinate system, the probabilities are 75% and 25%. But at this angle, they are 50-50. And at this angle, we can predict the result with certainty. For every possible state, there are angles at which the measurement is deterministic. Let's get back to our usual coordinate system. Squaring the vector components, we get the probabilities. But recall that in this video, we avoid the components. Instead, let's project the state vector onto the axes. The lengths of these projections give us the components, so we don't need to show them anymore. We can now describe the operation of the measurement device as follows. It breaks down the state vector into two parts, depending on how it's oriented in space. From the point of view of the device, the qubit state looks like this: the two projections that represent the two possible outcomes. When we activate it, it randomly picks one of them. And this determines the result. We got on in this case. And it becomes the new state vector. Let's run another example. We'll pick an angle. Here is what the device sees. We'll activate the device. It randomly picked off this time. And this is our new state vector. Here are a few more trials. Let's bring in a second qubit and a measurement device. This qubit has a state space and a state vector, and the rules are the same, of course. But now we want to treat the two qubits as a single system. If this were classical physics, then the two state vectors together would specify the state of the joint system. But in quantum physics, we need to take the tensor product of the two vectors. The resulting simple tensor represents the state of the two qubits together. Every simple tensor represents a valid state. Also non-simple tensors, but we'll get to that later. Here's another simple tensor example. We can derive from it the probabilities of both measurement devices. Here's one way to do it. We find out which two vectors created this simple tensor. These are the state vectors of the two qubits, and from them we can compute the probabilities. But we can read the probabilities directly from this visual representation of a tensor without breaking it down first. Before we do that, note that in our representation, the blue vectors are inside and the red vectors are outside. We could have chosen the opposite. Both visualizations represent the same tensor and contain the same information presented in different ways. But let's return to our original choice. This type of visualization allows us to see more easily the probabilities of the blue qubit. So let's put the red measurement device aside for now. But remember that this tensor doesn't really favor the blue qubit, and everything we show can be applied to the red qubit as well by using the opposite convention. We'll draw the axes of the blue device on the tensor. As before, we can rotate them. Also, again, the device sees two options, one on each axis. But now each option is a pair of blue and red vectors. The probability of each option is now encoded in the length of the red vectors. Again, we need to square them first. Now let's make a measurement. It randomly picked one of the two options. This determined the result on. The selected pair defines a new simple tensor, which is the new state of the system. And again, the device sees the two options that lie on the axes. Let's run it a few times. Let's show why this is equivalent to our previous description. First, we'll focus on the two vectors that created this simple tensor. Recall that these are the state vectors of the blue and red qubits. Let's look at just the state of the blue qubit. Previously, we computed the probabilities by projecting it onto our axes. Now let's look at the tensor's red vectors that lie on these axes. Note that they have the same length as the two projections. To see why, let's focus on the on option. According to our tensor construction rules, we obtained the length of the red vector here by computing this projection. Because of the symmetry, these two projections have the same length. So our red vector was scaled to have the same length as the on component. And similarly for the other axis, the red vector here has the same lengths as the off component. And we can use them to obtain the probabilities. Also, recall that in a simple tensor, all the red arrows are aligned. They are scaled copies of the red state vector. Let's set it, for example, to be horizontal. This means that the red qubit is in the off state, and there's a 100% chance to get an off result. Now let's return to the tensor representation and perform measurement on the blue qubit. Because all the red vectors are aligned, no matter which pair is chosen, the red qubit state remains horizontal. So the red qubit remained in the off state. This seems like stating the obvious. Why should the red qubit change its state when we measure the blue qubit? But now let's try a non-simple tensor. According to quantum physics, in a two-qubit system, any tensor is a valid state, including non-simple ones. We can't break down this tensor into two separate state vectors. This means the qubits can no longer be described as two separate subsystems. They can only be described jointly using this tensor. That's why such a state is called an entangled state. But we have a method now to interpret the tensor without breaking it down. As before, the blue measurement device sees two options. They have equal probabilities. No matter how we rotate it, they still have equal probabilities because all the red arrows have the same length. This means we have maximal uncertainty at all angles. It's harder to see from this visualization, but this is also true for the red qubit. It has a 50-50 distribution at all angles as well. But let's get back to focusing on the blue qubit. When we make a measurement, one of the options is randomly selected. And the new state is the simple tensor formed by the chosen pair. So measuring one of the qubits breaks the entanglement because we are back to a simple tensor. But let's return to our example entangled state. By setting the angle of the blue measurement device, we have some control over what the state of the red qubit will be after the measurement. This is sometimes called spooky action at a distance, or more formally, this is the non-locality of quantum physics. We make a choice here in the vicinity of the blue qubit. We choose some measurement angle. And this gives us control over something here, possibly very far away. Here are a few examples. By choosing this angle, we set the red vector to a diagonal direction, either up and to the right or down and to the right. And we got what we wanted. Here's an alternative choice. We now choose the red vector to be either horizontal or vertical. And again, we got what we wanted. At first, it may seem as if we can use this for faster-than-light communication. This is impossible, but entanglement can still be used for things that classical physics doesn't allow. See the description for a link to a video that discusses these points further. But here's a different insight the tensors give us about entanglement. This is a non-simple tensor. We'll call it the identity tensor, since each blue vector is associated with an identical red vector. We'll add an arbitrary coordinate system, and we'll now perform some modifications on this tensor. First, we'll scale the red vectors along the axes. That is, we'll stretch or contract them vertically and horizontally. We'll also allow scaling by a negative factor, causing them to flip along an axis. So here are some chosen scaling factors for both axes. Next, we rotate the whole object by some angle. And finally, rotate just the red vectors by some angle. It can be shown that any tensor can be generated using this sequence of 3 steps. This is a consequence of the singular value decomposition theorem. Let's demonstrate it with this arbitrary tensor. We start with the identity tensor, scale it by some specific scaling factors, rotate everything, and rotate just the red vectors. And we reached our target tensor. Now say initially we use a vertical scaling factor of 0, and we interpret this tensor as a quantum state. The red vectors are all aligned, meaning no entanglement. Also, if we measure the blue qubit at this angle, we can predict the result with certainty. This is also true for the red qubit. There's an angle where we can predict its result with certainty. Adding rotations doesn't change these two statements. The red vectors are still all aligned, and we can still predict the result with certainty if we measure at the appropriate angles. And now say the initial vertical scale is not 0, but a small positive factor. To make it a valid quantum state, we need to normalize it, so we need to shrink it horizontally a bit. The red vectors are pointing in different directions, so there is some entanglement now. But most of them are still almost aligned, especially the longer, more likely ones. This means that the entanglement is weak. And regarding measurement, we can still guess the result with high probability. This is the best angle we have in this non-simple tensor. Here too, the same is true for the red qubit as well, though it's harder to see from this visualization. And again, the rotations don't change that. And this is the other extreme. Here we have maximal entanglement, and we lost all information about the individual qubits. We can add rotations here too. So the initial scaling step controls a trade-off: information about the individual qubits, entanglement, or something in between. The rotations don't change our choice, but they make it a bit harder to see what it was. We can peel the rotations off using singular value decomposition. This basically amounts to finding the coordinate system where we see the largest red vector and rotate everything back. Let's conclude this section by viewing all maximally entangled states. We can also flip the red vectors vertically and obtain more such states. Now back to pure math. Here are 2 vectors again, and let's compute their tensor product. We can write it in a formula as follows. U and V denote our input vectors, and R is the resulting simple tensor. The symbol for the tensor product of individual vectors is usually the same as that for the tensor product of vector spaces. If we scale V by a factor of 2, then the result R is also scaled by a factor of 2. And we said before that scaling U has the same effect. We again get the same r scaled by a factor of 2. We can now explain why. Let's focus on these formulas. Imagine that u and v are not vectors but ordinary real numbers, and that the operation is ordinary multiplication, resulting in some real number r. The formulas still hold. They also hold if the inputs are vectors and the operation is a dot product or a cross product. A tensor product belongs to this family of operations as well. Later, we'll define this family more precisely and see that the tensor product is in some sense its most general member. And here's one more demonstration. We'll take a unit vector pointing in the x direction, some arbitrary red vector, and construct a simple tensor. Now let's switch to a rotated coordinate system. Everything looks rotated from this point of view, but of course all these objects remain the same. If we construct a simple tensor again, we get the same object. We can say that our visual construction method doesn't depend on the coordinate system at all, but that's not yet exactly right. Our method only works correctly with rotation transformations. Let's see how it fails with more general transformations. We'll switch to this coordinate system where the y-axis is tilted. This type of transformation is called shearing. We'll apply the same transformation to our tensor object as well. Our first problem is that the unit circle is no longer a circle, but that's easy to fix. To see how, let's go back to our original coordinate system and focus on our tensor. So far, we thought of it as an object composed of a unit circle and red vectors all around. But now let's think of it as a map that maps blue vectors to red vectors. The unit circle shows just a representative part of this map, but it extends everywhere. A tensor is not just any map, but a linear map. So a blue vector twice the size is mapped to a red vector twice the size. We can draw more circles representing additional parts of this map. Now let's apply our shearing transformation again. We can now draw a new unit circle representation for the transformed tensor. Let's examine, for example, a blue vector pointing upward. We can verify we got the correct red vector here by checking where it was before the transformation. But now let's construct this simple tensor from scratch. We got something different. Here's our example blue vector again. It's perpendicular to our input blue vector, so it is mapped to 0. But on the right, it is not mapped to 0. We'll fix this problem in the next episode.